Hello everyone, in this video we introduce 3D-GOI, a 3D GAN inversion method that enables multifaceted editing of scenes containing multiple objects. Multifaceted 3D editing of any object in an image is crucial and has significant applications in the film and gaming industries. Currently, there are few methods for generating complex 3D scenes, and editing such scenes remains unexplored. Therefore, 3D-GOI aims to fill this gap. The following image showcases a comparison between 3D-GOI and current editing methods, demonstrating that it can perform multifaceted editing on multiple objects. The core technical in 3D-GOI is GAN inversion. Next, we will introduce what GAN inversion is. GAN maps a distribution from the latent space to the image space using a generator and a discriminator and has been widely explored. GAN inversion is the reverse process. It obtains the latent code of an input image under a certain generator and modifies the latent code to perform image editing operations. Current 2D GAN inversion methods can be divided into three categories. Optimization-based methods directly optimize the initial code, requiring very accurate initial values. Encoder-based methods can map images directly to latent code but generally cannot achieve full reconstruction. Hybrid-based methods combine these two approaches. First, employ an encoder to map the image to a suitable latent code, then perform optimization. As shown in the left image, 2D GAN inversion requires mapping an image to a latent code. 3D GANs have an additional camera pose parameter compared to 2D GANs, making it more challenging to obtain latent codes for 3D GAN inversion. To achieve multifaceted editing of multiple objects, 3D-GOI needs to invert more codes, which is more challenging. As shown in the table on the right, n represents the number of objects. The generator used in 3D-GOI is Giraffe, as shown in the figure. It can control multiple codes to generate specific images. Its codes include properties such as shape, appearance, scale, translation, and rotation for each object, as well as the shape and appearance of the background and the camera pose. The task of 3D-GOI is to invert a given image into the corresponding Giraffe codes that compose it. By changing these codes, we can achieve multifaceted editing of the image. This is the overall framework of 3D-GOI. As shown in the upper half, the encoders are trained on single object scenes, each time using encoder loss to predict 1 omega, belongs to, while other codes use real values. The lower half depicts the inversion process for the multi-object scene. It can be divided into three parts. We first decompose objects and background from the scene, then use the trained encoder to extract coarse codes, and finally use the round-robin optimization algorithm to obtain precise codes. The green blocks indicate required training and the yellow blocks indicate fixed parameters. A straightforward idea is that the attribute codes of an object will map to the corresponding position of the object in the image. As shown in the image, the feature weight map of car A, car B in background where the redder regions indicate a higher opacity and the bluer regions lower opacity. By integrating these maps, it becomes apparent that the region corresponding to car A predominantly consists of the feature representation of cars A and B. The background's visible area solely contains the background's feature representation. Therefore, we can roughly separate different classes of code using segmentation methods. In this stage, we perform coarse estimation on the latent codes corresponding to the segmented images. We reverse engineer the structure of Giraffe's neural rendering to obtain our neural inversion encoder. Unlike typical encoder-based methods, it's difficult to predict all codes using just one encoder. Therefore, we assign an encoder to each code, allowing each encoder to focus solely on predicting one code. Hence, we need a total of 8 encoders. Pre-trained segmentation models have some segmentation errors and all encoder-based GAN inversion networks usually cannot accurately obtain codes, necessitating refinements. The optimization order is crucial due to the variance of the disparity between the predicted and actual values across different encoders, and the different impact of code changes on the image. For example, as shown in the left image, changes to background shape and background appearance codes controlling background generation mostly would have a larger impact on overall pixel values. Prioritizing the optimization of codes with significant disparity and a high potential for changing pixel values tends to yield superior results in our experiments. Hence, we propose an automated round-robin optimization algorithm at the right to sequentially optimize each code based on the image reconstructed in each round. Next, we present the results of 3D-GOI. First, we implemented editing of multiple attributes such as object shape, appearance, scale, translation, rotation, etc. on individual objects in the vehicle and CLVER datasets. Here we demonstrate multifaceted editing of multiple objects. As shown in the figure, due to our successful separation of multiple codes, we can achieve independent or simultaneous editing of any codes. The images show individual edits of two objects in the left and middle images and collective edits of the objects at the right images. We present a comparison of the neural inversion encoder with other 2D and 3D GAN inversion method encoders. As can be seen, our method outperforms all others, whether it is applied to vehicle data or face datasets. These are the quantitative results of the comparative experiment. The neural inversion encoder, whether used in Giraffe or the well-known 2D GAN style GAN, outperforms other GAN inversion methods in metrics such as MSA, PIPS, and ID loss. Here we present the ablation study of 3D-GOI. The table on the left shows the quantitative results of different attribute codes with or without the use of the neural inversion encoder. It's clear that the neural inversion encoder greatly influences the results, and the shape of the objects and the background in the code attributes is crucial for reconstruction. On the right are the results of the round-robin optimization algorithm. We found that prioritizing the optimization of codes that have a greater impact on the image content is more beneficial for overall reconstruction. Thank you all for watching. For more details, please visit our project homepage.